When printing a part on FDM is going to be a pain, SLA is the perfect alternative. Look at these linkages. Many of them are thin. They have small geometries and details, and lack any kind of obvious orientation for FDM printing. These are destined for the Form 4. I also knew the cylinders would be printed on the Form 4 because I wanted optical clarity, which can only be achieved with SLA, and Formlabs Clear V5 is arguably the best, most optically clear 3D printing resin out there. With the decision made on where all the parts would be printed, I mirrored the components that feature geometry specific to one side, which was only the cylinder, the crosshead/drive piston assembly, the crosshead guide, chassis, drive wheel C, expansion link, and support beams. My last step was to build the BOM for all the hardware and place the order with McMaster. Once the order was placed, it was time to begin printing. After exporting all of the parts as STL files, I first focused on the parts that would be printed on our X7 FDM printer. Some of the parts had obvious optimal print orientations, like the wheels, bearing blocks, and joining plates. However, other parts, like the support beams for the expansion link and lifting arm, as well as for the chassis, did not. I try to avoid support material as much as possible because it makes parts look bad, it requires extra post-processing, and it hinders dimensional accuracy. Therefore, I chose the orientation for the support beams that would minimize support material and thus maximize accuracy and aesthetics. But the print orientation for the chassis was still up in the air. When you're presented with situations like this, 9 times out of 10, the only solution is to split the part up. For the chassis, there's this really nice unified flat face, but this forward support beam for the crosshead guide is throwing us off. So I went back to this boss extrude and unchecked merge result to create a separate body. Then I just needed a way to join this body to the chassis after printing, which I plan to do with a hole for an M3x12 screw. Now, the chassis has an easy print orientation, the crosshead guide support beam does too, and will still maintain good surface finish and accuracy. For the drive wheel axles, technically there are 2 possible print orientations, but you would want to orient it this way to avoid a much taller support column that's going to consume more print material and more print time. With all the parts added to the build platform, I sent the job to the printer. While the X7 was printing away, I began setting up the other parts in preform for printing on our Form 4 SLA printer. Orienting parts for SLA printing is quite strange compared to FDM because we have to position them at these weird angles to minimize the peel forces during printing. I really like orienting parts at 45 degrees because it's a largely self-supporting angle, so the supports we add are mostly for securing it to the raft, stabilization, and maximizing dimensional accuracy. Using the auto-generated supports feature here in Preform makes this process really easy, and after they generate, I just go back and add a few more supports manually to get the most flat, square representations of our CAD models. With this build platform now packed with 24 parts, you can see the print time is 1 hour, 33 minutes using Gray V5. Why did I pack the platform with so many parts, you ask? Well, if I delete all of these parts except for our tallest one, the cylinder NPT pipe, the print time is basically the same. That's the power, or should I say magic, of masked SLA printing, the technology behind the Form 4. The LCD screen selectively masks off the UV light, so there's no print head or laser unit that's having to move around. So you can print lots of parts extremely fast and in the same amount of time. With these ready to go, I sent this job to the printer. And while the parts were printing, we got a special delivery. That's right. it's Formlabs' new curing station compatible with Form 4 size parts that heats and cures parts 3 to 5 times faster than its predecessor. I got it set up, plugged in, installed the glass turntable, and powered it on. The rotary dial has a super nice tactile feel, and all of the Formlabs resin curing profiles are pre-programmed. Now, if only we had some parts to cure. Oh, there's some. Dang, that was fast. The parts were looking really good, but we've got a couple steps before we're ready to cure and assemble them. After removing each part from the build platform, which was pretty easy since most of the rafts overlapped, so it just came off in one huge section, I manually washed them in isopropyl alcohol using this finishing kit. We actually have a Form Wash L that totally automates this process, but we didn't have enough solvent to fill it up, only enough to fill this bin, so that's what we went with. And Formlabs provides this finishing kit as an easy, low-cost option for those who need SLA printing but are a little tight on budget. After about 5 minutes, I pulled the parts out and placed them in the Form Wash L's wash basket for a quick hose down with fresh IPA, not to be confused with the tasty beverage. Off camera, I set up a box fan to let them dry for about 10 to 15 minutes. And now, we're finally ready to try our new Cure V2. I took some of the parts and placed them into the curing enclosure, selected Gray V5 from the profile, but before clicking start, I powered on our old Cure L, chose the Gray V5 profile on it, and loaded in the remaining parts because I wanted to see these two units race. With the increased UV power of the Cure V2, we're getting a 5 times faster cure cycle than before, which already was very fast. I think this Cure V2 is going to be our go-to from now on. The X7 continued to print overnight, so I could sleep well knowing parts were being manufactured hands-free and would be ready for action come tomorrow. And come tomorrow, the parts were looking really good thanks to Markforged's very own elite carbon fiber nylon. I was so happy with them, I even decided to give it a 5-star rating. I peeled off all the parts from the build platform and then got to work removing the supports from the drive wheel axles, the support beams, and the drive wheels. While in the groove, I also removed the supports from our resin parts, which flush cutters do well at removing at first, followed by a gentle tug thanks to the light touch support design implemented in preform. I like to then clean up any remaining support pips with the flush cutters. The 0.4mm clearance I modeled in was proving to be perfect for the mating parts, as demonstrated here by this connecting rod. To kick off the assembly, I installed the 8x16x5mm bearings into their bearing blocks, and then test fit those into the chassis, which was a perfect fit. Next, I installed the drive wheel axles into the drive wheels, which was a pretty tight fit and required a bit of fiddling, partly due to some flashing, or elephant's foot as we call it in the 3D printing world, and partly due to some stubborn support material that was left behind. Next, I installed the drive wheel and axle subassemblies into their respective bearings. Now, I didn't record this, but I actually had to reprint the drive wheel axles 2 other times to get their diameter just right so that it was a close fit with the ID of the bearings. Thankfully, parametric modeling and 3D printing make this effortless with 0 lead time, so I could test and iterate immediately and without any obstacles. I can now glue each wheel in place on the chassis, which held them fast so that each wheel could be spun to validate free range of motion. Next, I secured the connecting rod to the wheels after gluing the rod sections together. After drilling out the hole for the main rod to make it slide more easily around the crankshaft on drive wheel C, I positioned it on the wheel. Then I installed the lifting arm beam, which secures to the chassis using those hex nuts and M3x12 screws, along with the forward joining plate sandwiched in between. I then screwed on the forward crosshead guide support beam. I will say that in hindsight, I recommend screwing structural members like these into hex nuts rather than just into plastic to get a more secure fit. Next, I attached the crosshead guide and tested the motion of the crosshead within the channel, which moved nice and smooth. Again, 0.4 millimeter clearance is great for nice, smooth fits between 3D printed parts. I then secured the main rod into the crosshead using an M3x8 screw. After testing the motion, everything looks and feels really good. The next part I needed was the cylinder, which I hadn't printed yet, so I got that part and its head plate set up in preform, being careful to avoid any internal supports inside the bores and channels, and sent it over for printing in Clear V5. Clear is always fun to watch print because you can really see what's going on inside the printer. I've never really been sure how Formlabs manages to UV cure this material without curing everything around it, but they do it and they do it well. After they were washed and cured, I removed the supports from the cylinder and head plate. In its current state, neither the pistons nor their shafts would fit, so I had to drill out the shaft openings in the cylinder and sand down the shafts until they slid through smoothly without too much slop to cause excessive amounts of compressed air to leak through. Back to the model, I installed the expansion link beam and reverser center beam plate to the chassis. Then I test fit the radius rod and its small die block pin within the expansion link, which didn't have any obstructions, so I added a small bit of CA glue using a toothpick to set the die block in place. I then mounted the expansion link to its beam using a tiny M2x6mm screw. Next, I secured the combination lever to the valve piston shaft and then attached the radius rod to the combination lever. To bring everything home, I first attached the union link to the crosshead and then secured it to the combination lever. The movement of all of these linkages is free enough to allow for smooth spinning motion. All that was left was to attach the eccentric rod to the expansion link, secure the lifting link to the radius rod, screw the M3x30 screw into the lifting arm so that it can pass through the lifting arm beam, and screw into the reverse arm, making sure that they are oriented 90 degrees to each other. And finally, secure the lifting arm to the lifting link. Testing the motion after each major step was helpful to ensure screws weren't too tight and all the clearances were proper. I then screwed the screw post into the chassis so that I could finalize the reversing system. As part of this, we have that piece that rides the screw and pulls everything forward and reverse thanks to the hex nut slot in the top. I dropped in the M3 hex nut and screwed it in place. I then attached the linkage that links it to the central reversing lever, attached the central reversing lever to its post on the chassis, and then screwed the reversing wishbone to the central reversing lever. Once the wishbone was attached to the reverse arm using one of the numerous M3x10mm screws on this build, the reversing mechanism was complete. Before I could finalize the cylinder's attachment to the chassis, I first had to secure the drive piston and valve piston to their respective shafts. Separating the pistons from their shafts is another type of step that's required to bring digital models into reality, because without it, this model would be impossible to assemble. Both pistons required quite a lot of sanding since I set their clearances at only 0.1 millimeters or 0.05 millimeters on either side. That's because I wanted full control on how loose the fit should be to minimize air leak and maximize smooth travel through the cylinder bores. Now, I didn't record any sanding, mostly because it's boring as shit to watch, so I'll just jump straight to assembling the drive piston and valve piston. After screwing the cylinder onto the chassis, which again, looking back, I would have preferred to screw this into hex nuts, I tested the travel. This is exactly why I opted for printing the cylinders in clear, because I wanted this motion to be visible. My last linkage assembly step was to secure the eccentric rod to the eccentric crank using a short M3x5 screw, and then glue the eccentric crank to the keyed shaft of drive wheel C, which doubles as a stop to prevent the main rod from slipping off. I was really itching to test everything with compressed air, but first, I had to assemble the piping to the cylinder. Then I had to assemble the cylinder head plate to the cylinder using 9 M2x8mm screws. With my 2-gallon portable compressor on standby, I was now able to test the system. Doing this with only 2 hands was very fiddly because the hose is very rigid. I'm having to block off the other air port and ensure the assembly isn't flexing to avoid binding. It did run though, which was an enormous relief. However, the setup had to be just right. The piston had to be positioned in a specific location, and I had to blast a quick surge of air to get it going reliably. During most of my tests though, the wheels would rotate by only like 1/8 to 1/4 of a turn and then stop. The temperamental nature of the assembly made me question if I had done something wrong, because the valve piston was always in the same position when the wheels locked up, blocking off the steam admission ports. I began to wonder if the steam admission ports weren't positioned right or the valve dimensions needed to be altered. After rewatching some videos on steam locomotive function, I noticed that the animations also show moments where the valve piston totally occludes the steam admission ports. So, if my design was proper, then why was the system not behaving? Then it hit me. Steam locomotive drive wheels are quartered, meaning the position of the crank on one side is shifted 90 degrees from the other side. Why do they do this? To avoid the situation I'm dealing with right now. Steam engineers quarter the wheels so that the valve piston is always admitting steam on one side. One side might be closed off, but the other side is shifted 90 degrees forward or back so that the valve is admitting steam to the piston and the train can move forward or reverse. Fortunately, I knew this fact going into this design because I designed square openings in the drive wheel axles to accommodate some 4x4x12mm steel machine keys. Therefore, my problem would be solved by building the other half of the locomotive. Now, my responsibility to you, the viewer, is to not bore you to death, so we're going to speed run this part. Here are all the additional parts I had to print, including the mirrored components we discussed earlier. Here, I'm inserting the machine keys into the drive wheel axles to quarter them, and then attaching the other half of the partially assembled chassis together. I redesigned and printed the piping network, so I'm having to rethread the NPT coupler into this new resin printed part, and then mount the entire piping network onto the cylinders. By the way, you might have noticed the assembly sitting on that stand I designed. This was printed off camera. Everything was in place and rolling nicely, although there was some friction present, so I bought a can of silicone lubricant and sprayed it inside the cylinder bores, on the piston shafts, and inside the crosshead guide. I then buttoned everything up by screwing the cylinder head plates onto both cylinders. How's that for summarizing 4 days worth of work? Back to testing, this time using a much lighter gauge hose, I began pumping in air and it works. I was thrilled because even though your model might be square to the world in CAD, the physical world just introduces so many potential errors, so almost anything could foil the function. After a successful full throttle forward test, I ran this screw to bring the radius rod further up in the expansion link to simulate the locomotive in reverse. With a burst of air, the model fired into reverse, confirming my Walshurt's valve gear is properly set up. Now, I mentioned just a moment ago about the errors introduced in the physical world. I spoke at the beginning about the drive wheel axles having to be printed a few different times to really nail down the diameter needed to produce a close fit between them and their bearings. Well, I ran through several iterations amongst various other parts for this project until they were just right, or in some cases, where something unforeseen cropped up. Take the original design for the eccentric rod and eccentric crank. As these rotate, everything looks fine until, well, yeah, I didn't check for interferences in SOLIDWORKS. Otherwise, I would have caught this. But it gave me an opportunity to make a small but much needed dimension change to the eccentric crank and an easy modification to the eccentric rod to get everything working right again. Also, the reversing slide with the slotted hex nut had too much slop because the head of the screw here could shift. So I modified the design to add this tab that holds the screw in place and greatly increases the positional accuracy of the reversing mechanism. It just goes to show that a perfect CAD design can still produce an imperfect manufactured product. That's why testing your designs with small 3D printed models is really helpful for weeding out these hidden issues long before you jump into mass production. But that is all from me on this one. I really appreciate y'all for sticking around since this was a pretty long session, but I had a lot of fun with this project and learned a ton, and I hope y'all found it interesting and educational too. I also gained mad respect for those design engineers who managed to build the largest steam locomotive in the world with just pencil and paper. I read that the original blueprints consisted of over 2,000 handmade drawings, and that the erecting diagram used to build the locomotive was almost 13 feet long. Just crazy stuff. But this project is technically not complete because, as you saw, the big boy has a second set of driving wheels. So you'll have to keep an eye out for a potential part 2. Bye for now.